All right, guys, welcome back to our CCIE study sessions. We are actually going to be jumping into our discussion about the rapid spanning tree protocol. I know it says that this will take about 2 hours, but it actually probably won't take too long because we actually covered a lot of the concepts of spanning tree in the first session. Our focus really on this session is, what are the fundamental differences between 802.1d, which is the original version of spanning tree that we talked about. We talked about the whole election process and how the spanning tree election process goes through the whole, finding the root bridge and then being able to find root ports and then being able to find the designated ports and so on. Obviously, rapid spanning tree in our topology it's actually relatively easy to implement. So the only thing that we really have to cover when we go through this concept of rapid spanning tree is to understand what the differences are between what happens when a topology change occurs versus what happens when a topology change doesn't occur. So I'm going to show you guys something really quick here. We did some spanning tree configurations on switch 1 the last time, and we just looked at basic ways of manipulating priority values and manipulating the port priority to influence path selection. We talked about the whole concept of different link costs and the IEEE link costs and so on. So if I do a show spanning tree, we can see that we're running IEEE spanning tree, which is the 802.d variant of spanning tree for Cisco, which is PVST+. And what I'm going to do is I'm going to shut down port 10. Actually, before I do that, let me do a quick debug. And let me see, let's do a debug. I don't want to really do all. Let's try synchronization, all right? So I'm going to go into interface Ethernet 10. I'm going to shut down the interface and do a no shut. And what we should see is the different transitions that spanning tree is going to go through as part of the spanning tree election process. We're not seeing it. Hold on one second. Who just joined? That sounds like Tim to me, because I hear his little baby. Hey,
Yep, I'm on.
hey, Timmy, we just started.
Two different things, Scott. You need to let people know.
What? I'm sorry?
We're waiting on you to start.
So what I was going to demonstrate here, if I do a show spanning tree, and we can see that port 10 is obviously not participating in spanning tree because the port is shut down. Actually, Ethernet 10 is turned on. Let me go ahead and shut it down again. Let's do an undebug all first and do a debug spanning tree. I don't really want to do an all because let's try... let's do an all, what the heck. Let's do events. That might show us what we're looking for. So if I go into interface Ethernet 10 and I shut down the interface and hopefully do a no shut, what I'm trying to show you is that, there we go, that's what I was trying to show you. So you see here that as soon as I shut down this interface, which was participating in spanning tree, we see that we generated a topology change notification. That topology change indicates that something happened in the spanning tree environment, which triggers an event that occurs, that gets propagated throughout the spanning tree domain. Now in 802.1d, it's has kind of a negative impact because all the ports that are participating in spanning tree, in this case, would then start to kind of try to figure out what's happening in the spanning tree topology and whether a loop is going to be created. And basically, we're just going to have to go through a whole reconvergence event. And notice here that we've kind of gone through that reconvergence. Ethernet 11 changed its port status based on the fact that Ethernet 10 went down. But it took a little bit of time because the topology change notification happened at 214.00, and the port 11 didn't go into a forwarding state until 214.48. So it took about 50 seconds for the convergence process to take place. Okay, and that's one of the things that we talked about with 802.1d is that it's a relatively slow process. It takes quite a bit of time for the topology change notifications to get propagated. With 802.1d, everything has to go up to the root, and then the root has to notify all the other switches in the topology that a change has occurred. And then we start to go through these different states. Now, if I bring this interface up and I do a no shut, so again, we just saw an event got triggered. So a new port joined the spanning tree topology, and that port immediately went into a listening state. Okay, so a topology change notification was received. The port went into a listening state. Now it's progressed into the learning state. This was a 15-second time stamp. So if you look at the timestamp for the listening state, 2:16:02 and about 2:16:17. So it was about a 15-second transition. And then when we went from the learning state into the forwarding state, we're looking at about another 15-second transition. So 2:16:17 to 2:16:32. So it took, again, not quite exactly 15 seconds, but so we're talking about even in a normal transition, when the port is actually sending and receiving BPDUs, it takes about 30 or 40 seconds for that topology change to take place. And that's our regular spanning tree. Now, if I come into the switch and I do a spanning tree mode rapid, this is the actual global command that's going to allow me to switch from regular spanning tree into rapid spanning tree mode. It's the only command that really you need to be able to affect the change. So I'm changing to rapid spanning tree, and you'll see that now we're starting to send and receive all these different proposals. This is part of the difference of regular spanning tree versus rapid spanning tree. The reason why rapid spanning tree is so fast is because of the way that it handles spanning tree transitions, using proposals and agreements and whatnot. And we'll go through the details of that. That's more of the theoretical concept that I'll talk about as part of the process. We're kind of seeing a lot of stuff happening here because obviously we have to generate topology change notifications on all of the interfaces because I changed the global operational mode of spanning tree on the switch to rapid spanning tree. I want to demonstrate the change in the convergence speeds for you. So let's go ahead and implement rapid spanning tree on the rest of the switch ports as well. Okay. Spanning tree mode rapid. All right. And let's do the same thing on the other switches in our topology. This is really literally the only command that you need to convert from 802.1d to 802.1w, or at least Cisco's version of rapid spanning tree. Everything else that we talked about in the last lesson with regard to the spanning tree algorithm and how do we elect the root bridge and how do we elect the root ports and designated ports and all those other concepts that we talked about in the last lesson still apply to rapid spanning tree because it basically uses the same topology information. It basically uses the same algorithm to decide what ports are forwarding, what ports are not forwarding, and so on. So let's do a spanning tree mode rapid on this switch. That will switch us over to rapid spanning tree on that switch, and then we'll do it on the last switch here. All right. Now there are some other enhancements to rapid spanning tree as well. Some of the other enhancements include the inclusion of uplink fast and backbone fast. In our next lesson, we're going to talk about the differences between uplink fast and backbone fast and what those components mean in spanning tree. That's our next lesson, which we're going to cover all of this, what we call the spanning tree toolkit, which is things like Bpdu guard, root guard, loop guard, and all the other enhancements that Cisco added to the spanning tree process. Okay. So we'll get into that in our next lesson. But let me go ahead and enable spanning tree spanning tree mode rapid on this switch. And what I want to do is I want to show you the difference between the transitions from what we saw when we shut down the port in 802.1d and brought it up. We had that 30-second process. So I'm going to do a shut real quick on this, interface Ethernet 1.0. I'm going to shut down this port. All right. We'll wait for the port to transition to down and do a no shut and see if we can see what happens in this case. So now you can see that rather than going into like the listening and learning states, we're seeing that we're transmitting the port actually initialized. It went into a designated port role immediately. So we basically went into a forwarding state, not immediately, but pretty close to immediately. We're still trying to figure out what's happening with the topology. So we're sending out all these proposals. And I'm going to explain what a proposal is in a little bit, but we're sending out all these proposals to let everybody know that there's a new sheriff in town, or at least there's potentially a new sheriff in town, because this switch is going to go ahead and claim that it's the root based on not seeing any other Bpdus. So if I do a quick do show spanning tree dash tree, we can see Ethernet 1.0 is a designated port. It's in a forwarding state. We can also see that we're running rapid spanning tree. All right. So as far as configuration goes, you still have the spanning tree VLAN X root primary and spanning tree VLAN X root secondary to influence the election process. You still have the ability to set the port priorities to influence how traffic is going to flow. And so everything that we learned the last time is the same. So the only thing that we need to understand now is what is it about rapid spanning tree that's different than 802.1d. Certainly for the lab, you're not going to have to know the theory. I mean, at a minimum, essentially, they're just going to have you make sure that you're running rapid spanning tree. But I think in the lab, at least in my experience, you would have had to know specifically how multiple spanning tree works, which is a lesson that we're going to do on next Tuesday. I think that's what we're going to try and work out. And by the way, for next Tuesday, let me pause the. All right. So in any event, rapid spanning tree protocol, which is 802.1w technically, is the IEEE variant of rapid spanning tree, or in Cisco speak, it's RPVST plus. It's an evolution to 802.1d, but really a lot of the terminology remains the same. A lot of the parameters that we configure are unchanged. So it is backwards compatible with the 802.1d version. And I know, Tim, you had mentioned something in the last session. You were talking about the concept of what happens if I mix, 802.1d and 802.1w or Cisco's versions of those. Not a whole lot. I mean, they use the same algorithm. They use the same priority values. They use the same election processes, port priorities. So they are compatible with each other, but you will see a detriment to the overall topology change timers, because obviously when you're commingling 802.1d with 802.1w, there's definitely going to be a timer mismatch, and there'll be some. It's basically you'll revert back to the worst case scenario. Okay, rapid spanning tree does perform a lot better. And of course, it includes all of the proprietary extensions that Cisco had. And a lot of those proprietary extensions that Cisco added are actually enabled in rapid spanning tree without any additional configuration. The reversion that I talked about from 802.1w to 802.1d, the effect of that is not global. It's not across the entire layer 2 domain. The reversion is based on a per port interoperability. So if I have most of my switches running 802.1w, and I might have one switch that's connected with a trunk or something like that running 802.1d, then I will revert back to 802.1d on the switch that's running W on that particular port. But that reversion means that we're going to lose all of the benefits that 802.1w incorporates. Okay. As far as support on different Cisco switches, it's a standard, right? It's going to be supported on all your entry-level switches and all your. I mean, it's been around for quite some time. I mean, on the 4500s and the 6500s, it's been around since 12.1. And on the 8500, it's not available, but there are other options with the 8500. One thing I want to make a note of, let me actually bring up a notepad here, is that with rapid spanning tree, there are some new states, and this would be more of what you might see on the written exam as opposed to on the lab, of course. New states and port roles for spanning tree. 802.1d, we had, if you guys recall, we had a disabled state, we had a listening state, and that was what I was just demonstrating in the debug. We have a learning state, we have a blocking state, and we have a forwarding state. All right. And if you recall, we talked about the different transitions and what happens as we move through these individual states. The state of the port does get mixed, you know, whether it's going to block or whether it's going to forward traffic. And the role that port plays in the topology, whether it's a root port, a designated port, or whatever, is going to depend on the spanning tree algorithm. There really is no difference from an operational standpoint of forwarding or blocking between any version of spanning tree. There's no difference between how those ports actually look and how they operate. And that's ultimately the goal of any spanning tree process, is to get into that blocking state or that forwarding state. Both, when a port is in a blocking state, it's going to discard frames. But we talked about this listening state. It's going to discard frames, but it's also not going to update its MAC address table. And then in the learning state, we're still discarding frames. We're still receiving BPDUs and sending BPDUs, but we are still in a blocking state. You know, effectively, we're still blocking frames, but we're updating our MAC address table in this particular case. All right. The real difference with 802.1w, well, one of the key differences with 802.1d and 802.1w is we still have kind of the same roles, right? 802.1w, disabled. Cisco defines that as a role. I don't really think of it as a role. It just means the port is shut down and then it's not operational. But we don't have a listening state anymore. They've gotten rid of that listening state. And the blocking state is now renamed to discarding. So that's a discarding state. Basically, it means the same thing. All right. There are some additional roles that are introduced though in 802.1w. And I'm going to actually do a little diagram and kind of show you guys how this works, because that's definitely something that a lot of people get confused about. There's an alternate and there is a backup role. Okay, these are backup. These are roles, not states. As far as the states, alternate and backup ports are still discarding, but they're two. We didn't see the alternate and backup roles in 802.1d. The roles that we had in 802.1d, if you remember, were just a forwarding port, a root port, a designated port, non-designated port. Okay. All right. So the role in 802.1w, because again, we're talking about the convergence times and the theory of 802.1w, it's now a variably assigned role to a given port. And I'm going to draw some diagrams that describes what that means. The root port and the designated ports still remain the same. Remember, the root port was the least cost path port to the root, and the designated port was the port that was connected to the switch with the lowest bridge ID on a shared segment. But the blocking port, like I said, is split into the backup and alternate roles. The STA, the spanning tree algorithm, is going to determine the role of the port based on the Bpdus that are being sent back and forth. But the thing to remember about the Bpdu is that there's always some sort of method to compare any two of them, either one I receive and one I send, or multiples that I receive, to decide whether or not one is going to be more useful than the other. We define that in spanning tree as something called the superior Bpdu. Ultimately, in the beginning, switches are going to try to claim themselves to be the root regardless, and until they get a superior Bpdu, and then they will relinquish that role, and they will then kind of subvert themselves to the domain and allow the spanning tree algorithm to go ahead and decide what role that switch is going to play. All right. There are two values, of course, stored in the Bpdu, and those values are considered the primary information that's necessary for us to be able to perform our election. All right. So we don't need to really go through the whole election process. I mean, I can kind of summarize it a little bit, but we don't really need to go through the whole process. We're going to elect the root bridge. Do you guys remember how the root bridge was elected? It was elected based on priority and MAC address, and the lowest values win. We choose the root based on the lowest bridge ID. After that, I go through and I decide what my root ports are going to be. Essentially, it's going to be any ports that provide the least cost path to the root, regardless of whatever that path might be. We add up those IEEE path cost values, and the cumulative path cost will determine what port is the designated port. So we go through, we decide what our designated ports are, our root ports are, and then every segment is going to have a designated port. All right. But let me talk a little bit about the two new port roles that we didn't see previously. All right. So I'm going to use this to just kind of draw a diagram. And we're going to be talking about the alternate and backup port roles, which we didn't have in 802.1d. These two port roles correspond to whatever a blocking port would have been in 802.1d. And it's a blocking port was any of the ports that didn't get defined as a root port, or they didn't get defined as a designated port. So a block port might receive Bpdus, but the port doesn't go into a forwarding state because it basically lost the election. So you might run into a situation where a blocked port receives a more useful Bpdu than the one it sends out on the actual network segment. The diagram will really help you understand this. It's kind of hard to describe without actually drawing a diagram. But remember that the port needs to receive Bpdus in order to stay blocked, because otherwise it doesn't know. Well, it would assume if I'm not receiving Bpdus on a port, the port's essentially going to assume that a loop will not be formed because maybe there's a host connected to that port or it's an edge port. So there's some confusion as to how we handle that situation. So Rapid Spanning Tree introduced these new port roles to kind of solve that particular problem. So let's say, for example, I've got a switch here. All right. And that switch is, let me do it a different way because it's going to take me forever to draw that. We'll just use a little box here to draw our switch. So I've got a switch here. I've got a switch here. I've got a switch here. Don't chastise me on my drawing skills here. But I've got three switches in the topology. This switch right here is going to be my root for the topology because it, has the lowest bridge ID. So that's the root in my topology. And then I have a couple of different links, that connect, where's my tool? There it is. Some links here that connect my switches to the root. So obviously in this particular case, that's going to be a root port. That's going to be a root port. RP and RP. Now, I might actually have some downstream switches as well. Let me see how I want to do this. Well, let's actually let's just create some additional links here first, and then I'll do another example with some additional switches in a little bit. So let's say, for whatever reason, this is just to demonstrate the example. Let's say we have some network segments that look like that. So maybe there's a hub here connecting these links, whatever. We could continue to keep drawing switches, but it'll just get more and more confusing. So we have to decide on this particular segment, how do I handle the discarding ports? In this particular case, all of the ports would basically be discarding, if you recall, because we already have two direct connections to the root from the uplink switch ports, right? Hold on one second. Assuming that's a shared link on that bottom, we still need to find out what the designated port role is going to be for that particular segment. A port is essentially defined as designated if it can send the best Bpdu on the segment that it's connected to. And that's not really the way that I described it the last time, but it's essentially what it means, right? Because of these three links that you see here, this link here, this link here, and this link here, we're going to select the designated port based on the bridge ID of the device that's connected to that segment. That's how we always decide what the designated port is on a particular segment. Well, that's based on the bridge ID, and whichever one has the lowest bridge ID, that port is going to become the designated port. Now, you might look at that and go, well, I don't really need a designated port on that segment because I've already got my root ports. But there still has to be an alternate path to be able to get to the root if the primary root port fails. So we kind of do a pre-election and identify what the designated port role is in the event that we have to go through some convergence or some change. So we're sending out superior Bpdus from the switch on the right. Let's just assume the switch on the right has the lowest bridge ID. All right. So in 802.1d, the bridge is linked together on a segment, like an Ethernet segment, to create that domain, that spanning tree domain. So like we learned in the last time, on any one of those given segments, there can only be one path towards the root. It can either go this way or it can go that way. And the designated port is supposed to be really the port that follows that best path. If there are two, then a loop is going to occur, so we're going to have to do some blocking and so on. So all the bridges that are connected to a particular segment listen to the Bpdus of each of the switches, and they're going to make a designation, or they're going to agree upon essentially what the designated ports are going to be. And the port then corresponds to a designated port for the particular segment. Okay? So in this particular case, this port would become designated right here because that bridge is going to be sending out superior Bpdus for the segment. This port is going to become designated port for that segment because it's going to be sending out superior Bpdus. I don't have interface numbers here, but let's just assume that that's the lowest port number, port priority. That guy is going to be the designated port for that segment. Okay? Nothing that we didn't learn before. But now, because we're using rapid spanning tree, there's two port roles that correspond to the blocking state of 802.1d, alternate and backup. As I mentioned, those are still going to receive Bpdus, but they're going to be blocking. All right, so let's describe what the difference is between an alternate port and a backup port. An alternate port will get a more useful Bpdu from a different bridge in the topology. So in this case, this port here, let me use a different color. Let me use purple, I guess. So this port here would be considered an alternate port. Now, I want to make this very clear. It's still a blocking port. Alternate and backup ports in rapid spanning tree are still blocking ports. So we're still not sending or receiving traffic. But the reason it's defined as an alternate port is because it's an alternate path for that switch to get to the root. Does that make sense? It's an alternate path for this designated port link to be able to get to the root. So if this port fails, then we can simply move over to that other port, and we've kind of pre-identified that port as an alternate port. Now let me explain what the backup port is. Right? A backup port is a port that gets a more useful Bpdu from the same bridge, and that port's also a blocking port. So this port here would be the backup port. All right, still blocking, but it's a port that exists on the same bridge. The reality is, I mean, in the real world, you don't have to concern yourself too much with this, because all of this stuff is done automatically. And quite frankly, you're not really going to have a topology like this where you're going to see multiple segments connected together to provide this redundancy. But you may have to define in the written exam what the difference is between an alternate port and a backup port. And you'll actually see that if you do a show spanning tree. You'll see a designation of that in certain iOS images. I don't know if GNS3 is going to show us that, but all right. So that becomes the backup port because it is attached to the bridge that has the designated port for the segment. All right. Is it possible to only have a backup port or to only have an alternate port? Absolutely. It just depends on how the devices are physically attached to each other. All right. The distinction is actually already made with 802.1d, but this is how essentially there's a feature in spanning tree called uplink fast, and the rationale is that the alternate port provides an alternate path to the root bridge, and it can replace the root port if the root port fails. We're talking about from the switch's perspective on the right. The backup port is going to provide a redundant connection to the same segment, but it doesn't necessarily guarantee an alternate connection to the root bridge. So it's actually excluded from what we call this uplink fast group. And we'll learn more about those technologies, all the spanning tree toolkit technologies, as we get into our next lesson. All right. The whole point about this, right, and this is the whole concept, is that all of this is supposed to allow for rapid spanning tree to calculate the final topology for the spanning tree using essentially the same criteria as 802.1d, but when a topology change occurs and when topologies occur, when changes occur in the topology, links go up and links go down, we're able to recover from those changes in a much faster way, much faster state. Let me demonstrate that. So we already saw in our example when we shut down a port and we turned on a port in 802.1d, it took about 30 seconds for that process to take place. And we saw that from the timers in our normal spanning tree topology change notification. So here's our listening state at 2:16:02, and here's our learning state at 2:16:17. And then finally, we're in a forwarding state at 2:16:32. So, we're looking at essentially 30 or 40 seconds before the transition took place. Now, if I go into interface Ethernet 1.0, I think I'm already there, but I'll just make sure. And I do a shut. And try that shut. There we go. And I do a no shut. And I do a show spanning tree. Spanning, now let's see if I can do it quickly enough. Do show, I'm going to have to do that again. Let me do that again, sorry. Shut, because I wouldn't have done it fast enough. And a no shut. Do show spanning tree. Now you notice for Ethernet 1.0, it went into a blocking state. And it's still in a blocking state. But because it's still trying to figure out what's going on. I should have done my undebug all for this, but all right. So now it's moved into a learning state. Remember, we had a listening state previously with 802.1d. We skipped that 802.1d learning state, and now we're in a forwarding state. So it's a much faster transition. It actually would be even faster if we weren't using Ethernet. But it's a much faster transition than what we saw with 802.1d. All right, probably didn't seem like that because of the way the interface state changes in GNS3 and so on, but it's much, much faster. There is absolutely no change in the way different bridges and port priorities are used in spanning tree. The name blocking is used for the discarding state and Cisco implementations, with 802.1d we still had the listening and learning states. All right. The new features, though, is where the differences come in between the role and the protocol, and that's what's going to determine for a particular port its current state. All right. It's perfectly valid for any port to be designated and blocking at the same time, meaning that we're going through some sort of transition about trying to figure out what's happening. In fact, we saw that. Let me scroll back up here. That the port transitioned to a designated port role. Let me see if I can find that mixed in here with my outputs. So there's my down. So right here, the port is in a designated port state. And if you look at the show spanning tree output for port 1, it's actually Ethernet 1.0 is still blocking. So it's entirely possible for a port to be designated and blocking at the same time, but that's just a temporary state. It just means that the port is in a transitory state and it's moving towards the designated forwarding state. It's trying to figure out what the heck's going on. Okay. The thing about spanning tree is there's really not a whole lot to troubleshoot. You know, you might see issues with the election process because maybe there are some data plane forwarding path issues where you don't have a VLAN configured, so spanning tree is not going to be running in that particular VLAN, but that's an easy thing to find out. If I do a show spanning tree, let me, why is it not letting me, hold on one second. So if I do a show spanning tree, say for, I don't know, let's just do, come on. And let me do an undebug all first of all. Show spanning tree VLAN 78, right? So I can tell that spanning tree is not running for VLAN 78 because I don't have the VLAN created and there's no spanning tree instance created because there's no data plane element configured for VLAN 78. Another thing to keep in mind is that because Rapid Spanning Tree does have some additional enhancements, there is a new Bpdu format. Not very different. A lot of the Bpdu components are the same, but we've added a couple of flags to the Bpdu format. There's a flag called a TC flag. Let me put this on the notepad for you guys. I did save the other notes from the last time. New Bpdu format. There's a flag that is called a TC flag, and that stands for topology change. Oh, should get tight. All right. And then there's also a flag called a TCA flag. And that stands for topology change acknowledgement. All right. These are defined in 802.1d, but Rapid Spanning Tree uses all 6 bits of the flag byte to perform different functions as well. So these were always bits that existed in 802.1d, but that field, that flag field, actually includes 6 bits. Actually 8 bits, excuse me. It's a whole byte. That field is a whole byte. So if I was to look at this from left to right, for example, the first bit, that's going to be my TC bit. And then the second bit is going to be my proposal bit. We'll talk about what that is in a minute. That's new to 802.1w. And then bit number 2, I don't remember what that one is. I don't think it's used. Bit number 3 is what we call a port role bit. And these are all the flags in the Bpdu. And this is where we define a port as, actually, if I remember now correctly, it's 2 ports. That's the first bit in the flag field for port role, and the other, because we have multiple roles, right? So 00 would be like, for example, unknown, and 01 would be alternate or backup. And we saw this when we look at the Wireshark capture with the BPDUs. 10 would be a root, and then finally 11 would be designated. So if you're doing a Wireshark capture, designated. If you're doing a Wireshark capture and you're looking at a BPDU, you're looking at the flag fields. Those 2 bits are used to describe the current state of the port. All right. The next bit would be the learning bit, I believe. I'm going to go back and verify this, but I'm pretty sure that this is correct. The next bit would be the forwarding bit. So this is really kind of just the state of the port. And then the next bit would be the, this is one that's new to 802.1W as well. It's called an agreement bit. And then the last bit is the TCA bit. Okay. So out of all of these different bits, only in 802.1D, only that bit and that bit are actually used for the spanning tree 802.1D process. Let me pull up the BPDU Wireshark capture thing again that we were looking at the last time real quick. Hold on one second. So this is what I was referring to with the bytes, the different bytes for the different flags, right? So only the first bit and the very last bit, I think I got them all right. Did I get them all right? Let me see. Make sure I got them all right. Looks like I may have made a mistake. Yep, I mixed up proposal and I mixed up agreement. That's not bad though, from memory. So this is the agreement bit, and this is the proposal bit. I didn't do too bad. It's kind of hard to remember all this stuff. All right, so only the first bit and the last bit are related to 802.1D. All of those other bits, rapid spanning tree. And you can see in this particular case, we are running rapid spanning tree, so we would see those bits listed. If this was an 802.1D frame, those bits would still be there. They would just be not applicable or not used. And that's how they would be defined. So, oops, nope, I made a couple more mistakes. Dang it. Agreement and then forwarding and then learning. Well, I actually did worse than I thought. Sorry about that, guys. So we had forwarding and then we had learning. This is why I should look these things up beforehand. So we'll take that out. There we go. Forwarding, learning, then port role, then proposal, then topology change. Okay. All right. Now we got it right. I'll save these notes in the rapid spanning tree lesson folder as well. Now, as far as the actual BPDU, it looks pretty much like an 802.1D BPDU. We've got protocol ID and protocol version, and then we've got the routes information, and we got the bridges information, and all of our port IDs and our timers. So everything else from that perspective is the same. The only thing that we're concerned about is these flag fields that have changed. All right. So the last thing I want to really talk about before we get into kind of wrapping things up is how do we handle proposals and agreements? What is the proposal and agreement mechanism? How do we encode the role and the state of the port in rapid spanning tree and so on? So lots of new bits. The full BPDU, we don't really need to go through all that, and we can kind of see it here anyway. We understand what those other fields represent, right? The 24576, for example, represents the bridge priority. The 10 represents the VLAN. The MAC address represents the base MAC address of the device. Tim, did you get a chance maybe perhaps to do that show spanning tree on your Nexus switches that we talked about the last time, where you were going to see if the VLAN was represented, even though you set the priorities to 0 and 1? You're on mute, buddy. You there, Tim? Okay, these may not be there. I'll ask him a question later. All right. All right. I'm just curious. We'll see if Tim shows up later and we can ask him the question again. One more important change in rapid spanning tree is the Bpdu is type 2. You can see that in the second list there, and version 2. Now what that means is that legacy bridges will actually drop this Bpdu format. 802.1W is backwards compatible with D, but D is not forwards compatible with W, so that's important to understand. It makes it easy for W to detect legacy bridges because they're going to see a type of 1, but of course it means that 802.1D switches will not be able to see the WBPDU formats. Okay. Now Bpdus are going to be sent every hello time. We can see the hello time listed here as 2. That's the same as it was with D. The difference in this particular case, though, is that the Bpdus are not going to be relayed. I'll explain what I mean by that. I'll draw a little diagram and kind of explain what I mean by that. The bridge that does actually relay the Bpdus is more than the actual bridge that's going to actually generate those Bpdus. That's the way it was when we were dealing with 802.1D. In 802.1W, that's actually not the case. A bridge actually sends the Bpdu with its current information every 2 seconds by default, even if it doesn't receive any Bpdu from the root. In 802.1D, it was more chatty because it was actually sending that information along with its own information, any relayed information along with its own information. There's also faster aging of information in rapid spanning tree. If I don't get hellos for 3 consecutive times, the protocol information can be immediately aged out. The max age timer expires. If you look at the max age timer on the Wireshark capture here, you can see it's set to 20, which would normally mean that it's 20 seconds. But in the case of 802.1W, we have a faster age out timer. It's only 3 times whatever the hello interval is. So now we're talking about 6 seconds. Bpdus are actually used as a keep alive mechanism between the switches as well. Whenever a switch considers that it has lost connectivity to a direct neighbor, especially a root or maybe even a designated bridge, if it misses 3 Bpdus in a row, it's going to basically consider that neighbor to be dead. That fast aging of the information is one of the deterministic timer values that actually allows rapid spanning tree to go into quick failure detection. If the bridge fails to receive the Bpdus from the neighbor, it's pretty sure, I mean, the switch is pretty sure basically that the connection to that switch is lost. In 802.1D, that could have meant that there was a problem anywhere in the path, and it had to do with how Bpdus were relayed and so on. So failures are actually detected much, much faster in rapid spanning tree. And actually on a physical link, if you have a physical link failure, that means that the line protocol status will go down on an interface. Then that means that the detection is going to be even faster. All right. Another concept, and we'll be wrapping up here pretty soon. I just want to make sure you guys understand all of the nuances of rapid spanning tree, because it is used in MST as well. So all the concepts that we're learning now are going to apply to multiple spanning tree as well. All right. Another concept in rapid spanning tree is that we accept inferior Bpdus. Let me draw another diagram here so I can kind of describe visually what this looks like. All right. So we've got a couple of, let's just do a triangle here. 3 switches to connect it together. All right. And let's say that this port is blocking, and this is where we see our loss segment, okay? In this particular case, obviously we have a loop, and spanning tree is doing whatever it needs to do to be able to mitigate that loop. But the concept of inferior Bpdus is something unique to a rapid spanning tree as well. It's what makes up another spanning tree element, which you can actually enable in 802.1d as an option, but it's built in to rapid spanning tree by default. It's a feature called backbone fast. And there's an engine that runs in spanning tree that allows this backbone fast feature to work. When the folks in IEEE folks decided to incorporate or to include mechanisms in spanning tree, backbone fast was originally developed by Cisco as part of the toolkit that Cisco wanted added to the spanning tree topology or spanning tree algorithm or process. 802.1w actually includes this backbone fast engine by default as well. So if a bridge receives an inferior Bpdu, inferior meaning that it actually has a higher bridge ID or it has a higher priority or whatever, anything that would make it less preferred. If it gets an inferior Bpdu from its designated port or the root bridge, it immediately is going to accept that, and it replaces the one that it previously had stored. All right, so what does that mean from this topology perspective? Let's say, for example, this is, let me draw it in black here. So this is switch B, this is my root switch, and this is switch C over here, okay? Because switch C, let's say that an inferior Bpdu is sent down here saying, I am the root. Okay, I am the root. So that's what we would identify as essentially an inferior Bpdu. Because bridge C still knows that the root is alive and well, all right, I shouldn't have drawn that red star there. It's going to immediately send a Bpdu to bridge B that contains, actually, let me back up here. The first event that would have occurred here, this was a blocking state initially. So this was a root port, this was a root port, meaning that B had selected that port as its root port and C had selected the bottom port as its root port. So that was our stable state. Then, that's what I should have drawn this later, this link goes down, all right? B is going to start claiming to be the root. That's what I was trying to demonstrate by saying I am the root. That is still considered an inferior Bpdu from switch C's perspective because switch C didn't lose connectivity to the root. Switch C still knows that the root is alive. So it's going to immediately send a Bpdu to bridge B that contains the information about the root. As a result, bridge B does not send its own Bpdu. Stop sending that inferior Bpdu. It accepts the port that leads to bridge C as the new root port because it immediately got that Bpdu that was forwarded from the root within 2 seconds, right? Or maybe even less than 2 seconds. So the convergence time was much, much faster. This is the concept of backbone fast. Again, it's something that you can turn on 802.1d, but it's built in to 802.1w or rapid spanning tree. I hope that makes sense. I kind of didn't do that in the right order, but I hope that that makes sense to you guys. You guys understand what I was referring to there. Okay? The rapid transition to the forwarding state is another component that was introduced in 802.1w. In our legacy spanning tree algorithm, we just basically passively waited for the network to converge before it turned a port into a particular forwarding state. The achievement of faster convergence was simply because we didn't really change the algorithm. We didn't make modifications to the algorithm. So the achievement of a faster convergence state was really just a matter of tuning the conversation or the conservative default parameters like the forwarding delay and the max age timers, those 15-second timers and 20-second timers, and put the stability of the network, well, if I were to adjust those timers, right? Maybe my goal is to converge faster. So I'm going to go ahead and say, you know, I'm going to reduce the max age timer and I'm going to reduce the forwarding delay timers to 2 seconds or 1 second or whatever. That would actually potentially cause issues. And what they did in rapid spanning tree is they were able to actively confirm that a port can safely transition to the forwarding state without having to rely on any timer configuration. So you will actually see in some cases where rapid spanning tree, we didn't see that initially when we shut down Ethernet 1.0, but you'll see it where rapid spanning tree will converge in a matter of a second or maybe 2 seconds. So even though we still have the same forwarding delay of 15 seconds for even the learning state, if topology changes occur, the convergence time is actually even faster. There's actually real feedback and a feedback mechanism that takes place between a rapid spanning tree switch and another rapid spanning tree. And the whole point is to achieve fast convergence on a port. And that's going to rely on two elements. Okay. Let me put that in the notepad as well. I'll just call this faster convergence. Say what? All right. And we have two new variables defined in rapid spanning tree. One is called an edge port, and one is called a link type. Now that's a little bit of a problem with GNS3. Because the link types are defined as shared link types as opposed to point-to-point link types. But I'll explain a little bit about what a shared link type is. Let me describe what an edge port is first. It's pretty simple. Okay, an edge port concept is basically really just a port that you would normally have, say, a port fast feature turned on. Any port that's directly connected to an end station, something that's not going to create a bridging loop in the network topology, that's going to be considered an edge port. So an edge port will usually directly transition into the forwarding state, and it's going to skip the listening and learning stages if you have the port fast feature turned on. Edge ports, port fast ports, they don't generate topology changes or change notification either when the link toggles. So if I go into a switch port, I'll demonstrate this. Port fast is not unique to 802.1d. It exists in all versions of spanning tree. But if I go into interface Ethernet 1.0 and I do spanning tree mode port fast or spanning tree port fast enabled, I think it's just spanning tree port fast. I've configured a feature on that port that forces that port to transition to a forwarding state immediately. So if I do a shut and wait for the port to go down, all right, and I do a no shut and I do a show spanning tree, you can see that port 1.0, there we go, port 1.0 went into a forwarding state immediately, and it was identified as an edge port. It'll eventually lose that state, by the way, because this is a link that actually goes, if I look at my topology, 1.0 is a link that goes to another switch. So it'll lose its edge port status, and it'll lose its port fast status once it starts to get a spanning tree, some spanning tree messages. Actually, let me see. It should. Let me see something. Do show interface trunk. That's why. Because it lost its trunking status when I did a port fast configuration. So we've got ISL on here. It's doing some weird things. But it would, any kind of port fast port would lose its port fast status if it receives a Bpdu, and it becomes a normal spanning tree port. Yeah, go ahead. Hello? Say it again. It was kind of breaking up a little bit. Oh, Tim, I see your chat message there. Not sure why you couldn't hear me. Anyway, on the Nexus, putting a 1 in rapid spanning tree as a priority is accepted, but it automatically changed it to a 0. Oh, I see what you're saying. Yeah, so it still enforces the 4096 rule, but it allows you to put in a 1, and it takes basically the lowest value. So I'm curious if you put in like a 4095, if it would drop it down to a 4096. If you put in a 4097, if it would drop it down to like a 4096 or something like that. Yeah, sorry about that. I didn't see the chat there. Yeah, I think we're having a little bit of bandwidth issues with audio. Hopefully you guys can hear me okay. Derek just arrived, so say hi, Derek.
Hey, guys.
Oh. Anyway, edge ports, any edge port that receives a Bpdu, it's going to lose that edge port state. I don't know why it didn't in this particular case, but and it's going to basically revert back to a normal spanning tree port. There is a user configured value and an operational value for the edge port state. Like I said, the port fast option is how we implement that. Two ways that you could do that. You could do spanning tree port fast default, which is a global command, and that's going to enable port fast on all interfaces that are non-trunking ports. Or you could go into an interface and enable it exclusively on the interface by saying spanning tree port fast. There's actually also an option. There we go. There's also an option to enable spanning tree port fast on a trunk interface as well, which you may decide to do if you have an edge port that connects to like a VMware server or something like that. My intent wasn't really to talk about port fast in this case because we're going to talk about that in our next lesson, all the spanning tree toolkit pieces, but anyway, doesn't hurt to see it more than once. All right. The other thing I had mentioned was the link type. Rapid spanning tree can only achieve its transition rapidly to a forwarding state on those edge ports and on point-to-point links. So if I have a topology, and this is where GNS3 kind of falls short a little bit, because what I should be seeing if I do a show spanning tree, I should be seeing these as P2P, the letter P, the number 2, and the letter P. Because they're supposed to be point-to-point ports. The reason why they're showing as shared is because they're half duplex. In GNS3, the Ethernet ports are going to show up as half duplex ports, so they're going to show up as shared ports. So any link that goes between two switches that's like fast Ethernet or gigabit Ethernet, that would be considered a point-to-point link. Anything that's connected to a hub or some half duplex connection, that's going to be considered a shared link. Okay. The link type is automatically derived from the duplex of the port. All right. So any port that's going to operate in full duplex is going to be assumed to be point to point. Any half duplex port is going to be considered as a shared port by default. I've never tried this. Let me see. Interface Ethernet 1.0 duplex full. I want to see if we can trick it. Show spanning tree. Yeah, it's still looking at it as an edge port. So unfortunately with GNS3 and these Ethernet switches, it's kind of misreporting the representation, but that's okay. All right. You can actually override the automatic link type settings with an explicit configuration, but most links are going to operate in full duplex mode, and they're going to be treated as point-to-point links in rapid spanning tree, which means in the terms of 802.1w, this is going to make them adequate candidates for rapid transition to a forwarding state. Okay. We already talked about essentially how the convergence works with 802.1d. But I do want to kind of go through the process real quick. This is the last kind of thing that we'll talk about tonight, and then we'll wrap it up. I'll show you some other things a little bit later on, okay, in our next lesson. Sorry about the dog barking. Okay. So, hold on. All right. So, let me draw another diagram here. Mike had a question. Bpdu guard would just error disable a port then, otherwise it would still keep it as an edge port. Yeah, we'll talk about Bpdu guard in the next lesson, but to answer your question, Mike, yes. If you enable Bpdu guard on a switch port, any reception of a Bpdu, regardless of the port state, would result in the port actually error disabling. So it doesn't matter if it's rapid spanning tree, it doesn't matter if it's an edge port, it doesn't matter if it's a point-to-point port, it's going to result in the port error disabling. And I will show you guys that, of course, the next time we get into the toolkit. All right. So let me go ahead and draw a little diagram here. Let's see. This guy's going to be my root port or my root bridge. This will be bridge A, so we'll have a link there. This is bridge B. This is bridge C. Let me think. Do I want to add any more to this topology? It doesn't really matter. We can. Let me actually add one more just to make it kind of demonstrate the concept here. I'm going to add a switch D here. And we'll put some sort of LAN in here. So in this scenario, all right, new ports are coming up on the route. And switch A, in this case, there's going to be, that port on switch A is going to basically be immediately put into a listening state, and it's going to block traffic, all right? Bpdus from the root are going to start propagating towards the leaves, going down to switch B, switch C, and switch D through A. So let's walk through the scenario here. In this particular scenario, a link between the root bridge and bridge A gets added, all right? So this link right here, we added this link to the topology. Before there was another path through the little cloud there, but now we've added this link. Suppose there was already an indirect connection between bridge A and the root bridge. In this case, that would have gone through that path, right? Remember, I'm talking about 802.1d in this case, not 802.1w. Spanning tree blocks the port and disables the bridging loop on that interface. That's the purpose. All right. And then as the ports come up, both ports on the link between the root bridge and bridge A go into a listening state. So they're still blocking, but they're now in the listening state. All right. Bridge A is now able to hear from the root directly, because even though the port is blocking, even though we're not processing frames, we are still sending and receiving Bpdus. All right. So we're able to hear from the root directly. It immediately is, that means it's going to immediately propagate a Bpdu on its designated ports towards the leaves of the tree. So as soon as bridge B and switch B and C, so we're propagating those BPDUs down the chain. Sorry about that, guys. As soon as the superior BPDUs are sent down, B and C are going to receive those superior BPDU information from bridge A. They're immediately going to then relay that information towards the leaves down the line, right? And as soon as bridge B and C receive that new superior information from A, that means that we're now going to start to go through the re-election process, all right? So what's going to happen in this case is as this propagates, this port here is now going to transition into a blocking state, and then that's going to propagate back up the topology. So the BPDUs from root switch D, the BPDUs arrive on switch D from the root. That immediately puts that port into a blocking state. Spanning tree is pretty quick, right? Even in 802.1d, this propagation doesn't take very long. It is pretty quick in how it converges and how it calculates the new topology of the network. The only problem now is that we've gone through something called twice the forwarding delay before the link between the root and bridge A eventually end up in the forwarding state, right? Because we have to go through the listening and we have to go through the learning state. And if you recall, those timers were 15 seconds each. So we have this 30 seconds of disruption of traffic, and the entire A, B, and C part of the network gets isolated, right? Because now we've blocked this port down here, and these ports are blocking, so we've kind of isolated the rest of the network. That's why when you say in 802.1d, when a topology change occurs, it affects the entire layer 2 topology. There's no actual feedback mechanism to clearly advertise that the network should not kind of respond in this way, if you will. All right? So the last thing we'll take a look at, I promise this is the last thing, I know it's late there. So the last thing we're going to take a look at is a similar topology, but in this case we're going to take a look at it about how it would react if it was rapid spanning tree. Remember, the final topology is going to ultimately end up being exactly the same because the election and the algorithm is exactly the same. They're going to have one blocked port in the same place as before. It's just that the steps that are used to reach that topology have actually changed, all right? So let's walk through that scenario. So both ports on the link between A and the root, they get put into the designated blocking state. We saw that when we did the debug on our switch when we were running rapid spanning tree. They go into this designated blocking state as soon as the interface comes up. So far, that's kind of like 802.1d. We're blocking the ports. The ports know that there's a topology change that occurred, and we're trying to figure out what's going to happen. But this is where everything diverges from what 802.1d does. At this point, a negotiation is going to take place between switch A and the root. As soon as switch A receives a BPDU of the root, it blocks the non-designated edge ports. And there's a term that we use to describe this process, and it is called sync. All right. Once this is done, the non-designated edge ports, by the way, are the ones below, right? These two ports here. So rather than propagating everything down to D, switch A is kind of trying to figure out, okay, how is this going to affect the topology? Okay. Once this is done, bridge A explicitly authorizes the root bridge to put all of its ports in the forwarding state because now A has said, look, you're not going to cause a loop. I've blocked all my non-edge designated ports, non-edge meaning no hosts. So I'm not going to block the host ports, but my designated ports. So I've gone through and I've blocked all my designated ports. Then it tells switch A, go ahead and put your, let me change the diagram here to represent that. Go ahead and put your ports in a forwarding state. So now we're kind of at phase number 2 here. So this guy's in a forwarding state, and my non-edge designated ports are now in a blocking state. Okay? So the link between switch A and the root bridge is propagating traffic. Once switch A blocks all of the non-edge designated ports, the normal traffic can flow between the root and switch A. There still could be a loop if we didn't handle the traffic correctly. There still could be, there still can't be a loop in this case because those two ports are blocked, right? That loop would occur, of course, from here, going around the root to switch A, which can't happen in this case now because those non-edge designated ports are blocked, okay? So instead of blocking above switch A, the network blocks below switch A. It just means that the potential for a loop gets cut out at a different direction. And essentially what happens is that change propagates down the path until we build our final topology. So A is going to send out now those superior BPDUs from the root. B, of course, is not going to make any change because all it has is edge ports. C is then going to immediately block the non-edge designated port. And then, well, this link here, these links here would go into an immediate forwarding state. You kind of follow what I'm saying? I didn't really draw that very well, but essentially we're kind of creating this chain reaction where the propagation of these non-edge designated ports get blocked as I go down the list until I get to my final state. All right, so in this case, switch C only has to block its designated port to switch D, and that means eventually we get into our final topology. Remember that the final topology is exactly the same as the example that we went through before, which is 802.1d. So P1 on port 1 on switch D ends up blocking. So the final network topology gets reached, and it only takes the amount of time that it's necessary for the new BPDUs to travel down the tree. So instead of 30 seconds, you might at worst case be talking about 2 seconds here, and maybe another 2 seconds, or maybe even 3 seconds here, but that's where we get that much faster convergence time. There are no timers involved, right? We're not waiting for listening or learning timers to expire. We're not using that 15-second count. The mechanism is just a matter of the hello time. All right. The only new mechanism that was actually fully introduced by Rapid Spanning Tree is the acknowledgement that a switch can send on its new root port in order to authorize an immediate transition to the forwarding state, which bypasses that whole concept of twice the forwarding delay for that time period. Okay. All right. This only works on point-to-point links. That means that they have to be full duplex links. Edge ports, you might think edge ports don't really play a role in this case, but they actually play even more, a more kind of an important role in this place because if you fail to properly configure an edge port, the connectivity could be impacted by the link between switch A and the root coming up. All right. So the last piece I want to talk about is the proposal and the agreement sequence, and then we'll wrap it up. I think we pretty much covered everything that you really need to know about Rapid Spanning Tree, but I do want to talk about one more thing. It's called the proposal and agreement sequence. If a port is selected by the spanning tree process to become a designated port, even if it's a designated port, we know designated ports eventually end up going into a forwarding state. We're still going to have to wait twice the forwarding delay, which is 15 seconds times 2, before it's actually going to transition to a forwarding state. In Rapid Spanning Tree, we still have the concept of designated, but we combine the concept of designated with the blocking state. And we achieve this fast switching to the forwarding state by these proposal and agreements. I don't really need to draw a diagram for this, but I can kind of walk you through through the process. When we did that debug, we saw that the port Fast Ethernet 1.0 was a designated port in the discarding, actually was in the discarding state originally, but it went to the learning state, which actually is a discarding state anyway. It sets the bit, and if you recall, in the flag fields, there was a bit in there called the proposal bit, okay? It sets that proposal bit in the Bpdu that it sends out. That's what occurs for, say, on this topology, if this link is coming up, I'm sending out a Bpdu with that proposal bit set, okay? And that's going to move down the switch stack. Because switch A in this case receives the superior Bpdu information, it immediately knows that port 1 is the new root port. So then we go through the whole sync process. Switch A then starts the sync process to verify that all the ports are in sync with this new information, and so on. So the port is in a blocking state, which means it's discarding, but we're still kind of going through the process, the election process. I guess the bottom line here really, guys, is that we have, in 802.1d, everything was a response to information that was being passed up and down the tree and forwarded, these Bpdus. In rapid spanning tree, we have other types of Bpdu communications, and I don't know that it's really necessary to kind of go through the rest of the details, but the agreement flag, the proposal flag, this is what's used to allow switches to actually negotiate the speed of a particular port or the transition of a particular port. All right. I'm trying to think. There's probably one more thing I should mention. I was trying to think about whether or not I wanted to talk about the agreement and proposal process, but let me go through one more thing. All right. I keep saying that, but I promise this is the last thing. In 802.1d, whenever 802.1d detects a topology change, it uses a notification process, and I was describing this right when we started the class today, to notify the root bridge of that topology change. So regardless of however far down the change occurred, it could be 4 or 5 or 6 switches below the root. In 802.1d, we notify the root bridge first. So that has to propagate up to the root. Once the root bridge becomes aware of a change in the topology, it's what the root bridge is the one that sets the TC flag in the Bpdus that it's going to send out, and then that gets relayed to all the other bridges in the network. So you can imagine could be a rather slow process. If a bridge receives a Bpdu with the TC flag bit set, it sets the bridge table aging timer to the forwarding delay time, which is 15 seconds. So it's flushing its state information, any of its stale information, and the topology change mechanism is propagated, right? So it's a really, really slow process. In rapid spanning tree, we do this a lot more efficiently. Only non-edge ports, remember an edge port is where hosts are connected, that move into the forwarding state will cause a topology change. So if I plug a computer into an edge port, it doesn't force a topology change notification. If a port's already blocking, and it's, well, I don't know how that would happen, never mind. But only non-edge ports, if they move into a forwarding state, that's going to cause a topology change. That means that you had some sort of loss of connectivity. Maybe if you had a loss of connectivity on a port, that's not considered a topology change anymore in rapid spanning tree. So a port going down in 802.1d would cause a topology change notification just like a port coming up. It kind of makes sense though if you think about it, right? Because if a port goes down, it's not going to create a loop, right? Only ports coming up could create a loop. So when rapid spanning tree detects a topology change, several things take place. It starts something called the TC while timer, which is a value equal to twice the hello timer on all of its non-edge designated ports and its root port. It flushes the MAC addresses associated with all those ports, and then we start to propagate the topology change information. So when a bridge receives a Bpdu with the TC bit set from a neighbor, in rapid spanning tree, it clears out its MAC address tables that it learned on all of its ports, except for the one that it received the topology change notification on, because that port's still active. It starts that while timer, and it sends out Bpdus with the TC value or the TC bit set on all of its designated ports and its root ports. Rapid spanning tree doesn't use the TCN bit anymore, only uses the TC bit, unless it needs to notify like a downstream 802.1d switch or something like that. Basically what I'm trying to get at, and maybe I should have drawn a diagram, it might have been more efficient, but is that the TCNs flood very quickly across the whole network. And this whole propagation of the TC is only a single step. Rather than sending everything up to the root bridge and then having the root set the TC bit and then flood that information down to the rest of the network, the topology change notifications get sent out much, much faster. So there's no need to wait for the root bridge to be notified and then maintain the topology state change for the whole network for that deterministic amount of time. All right? In just actually a few seconds, basically because these TCNs or TCs are set in the Bpdu, just a couple of different hello times and the entire, all the cam tables and the entire further VLAN are flushed, and then we start learning where everybody exists from that point forward. Okay? All right? So I guess that's about it. Compatibility with 802.1d, it's still compatible. It's just keep in mind, like I mentioned before, if you're running 802.1w and you put an 802.1d switch in the topology, you're going to lose all those benefits, those fast convergence benefits of 802.1w, but it's on a per port basis, right? Obviously, the best recommendation is not to commingle 802.1d and 802.1w, all right? I know that this particular lesson didn't involve a whole lot of hands-on, but that's because we already learned all the fundamentals of spanning tree in our last lesson, all right? As I mentioned before, really the only thing that's necessary in order to enable rapid spanning tree is the spanning tree mode rapid command. All the other commands that we learned in the other lesson with regard to changing priorities and all that apply both to spanning tree and rapid spanning tree. All right? So let's talk a little bit about what we're going to discuss the next time. It's a section that I skipped over because it's a little bit more complex. Optional spanning tree features. So in this case, we're going to be talking about Bpdu guard. We're going to be talking about Bpdu filter, root guard, loop guard, backbone fast, uplink fast, ether channel guard, all the other ones, right? What we call the spanning tree toolkit. And then we have one more lesson on spanning tree. And then we have, so that'll probably be our next lesson. We've got the optional spanning tree features, and which we'll probably do tomorrow. And then this multiple spanning tree protocol discussion we'll do next week, early next week. And then we'll wrap up our switching stuff next week, and we'll start to get into the routing topics. All right. All right, guys. Do you guys have any questions? Did you learn anything today? I know it was a lot of theory, but you know what? All right. I can't hear anybody, so I'm assuming everybody's good to go. Probably already all asleep already. Hello, hello. Everybody there?